Hi Sarina, thanks for asking your question. I'm going to briefly explain why computers only work with two numbers, 1 and 0, and also how computers are able to do all sorts of powerful and amazing things with only these two numbers. To start, the first thing we need to understand is what a computer actually is. A computer consists of many millions of small electrical components. These components all work together to control your keyboard, your monitor, your hard drive, and a bunch of other stuff. But the part of the computer that does the actual computing or processing or number crunching is the microchip, or what's also called the CPU. A microchip consists of millions and millions of what are known as transistors. Transistors are teeny tiny electrical components, much smaller than the diameter of a human hair. A computer microchip can pack millions and billions of transistors into it, thanks to an innovation in the 50s that allowed transistors to be made from silicon. That led to the computer revolution, and also why we call the San Francisco Bay Area Silicon Valley. Transistors are very small, and as a result, very simple. They can only do one basic thing, which is hold an electrical signal in one of two states, high or low. High, low, like 1 and 0. So a computer uses ones and zeros because its constituent hardware components, transistors, are able to represent ones and zeros as high and low signals. The way a computer does complex stuff is that it can read and make decisions based on ones and zeros very, very fast. It seems magical, but all the complex stuff computers can do today, from recording videos, to playing chess, to letting you check your email, all of it is based on a computer being able to process and make decisions upon billions of ones and zeros streaming over the CPU very, very quickly. Ones and zeros are used for essentially two types of things on the microchip, representing instructions and representing numbers. A computer can follow a set of basic instructions, such as add, multiply, read from a place in the computer's memory, and jump to another instruction. Each of these instructions has a number or code that is a different arrangement of 32 ones and zeros. The other thing a computer uses, and essentially this is all a computer does, is manipulate numbers. Adding and multiplying them, using them as addresses for computer memory, using them to decide what instruction to execute next, etc. It's actually possible to represent any number you can think of with just ones and zeros. Take the number 27. Think of all the different ways you can write or represent the number 27. There's the normal way with decimal numbers 2 and 7, like we have here. You can use Roman numerals or tally marks. You can also write the number out in English, 27, or even in Gujarati, Satyavis. You can even express 27 as a mathematical expression, like 20 plus 7. Or even if you wanted to draw 27, you could arrange 27 blocks like this. Now let's look at this more closely. If I arrange these blocks in a certain way, I see that our decimal numbering system uses powers of 10. We see that the number 27 has 2 10s and 7 1s. So in terms of powers of 10, there are 2 10s, 10 to the power of 1, and 7 1s, 10 to the power of 0 in the number 27. But if you think about it, I could write this number in other powers, which are also known as bases. If I wanted to write 27 in, say, base 5, I would start out by first calculating the powers of 5. 5 raised to the power 0 is 1. 5 raised to the power 1 is 5. 5 raised to the power 2, or 5 squared, is 25. 5 raised to the power 3 is 125. Then I would start counting how many of each power is contained in the number 27. So how many 125s are in the number 27? 0, because 27 is smaller than 125. How about 25s? How many 25s are contained in 27? Well, 1. Okay? If I took out that 25, I now have 2 left over. 27 minus 25. How many 5s are in 2? Well, 0. How many 1s are in 2? 2. So now we can see that I can write the number 27 in base 5 as 102. We can do the same thing in binary, which is base 2 representation. Again, we start out by writing the powers of 2. Then we go through and ask, how many 16s are in 27? Well, there's 1. So 16, 27 minus 16 is 11. Okay, so now we have 11. How many 8s are in 11? Well, 1. 11 minus 8 is 3, so now we're left with 3. How many 4s are in 3? 0, because 4 is bigger. How many 2s are in 3? Well, we can fit 1, 2 in 3. We're left with 1. How many 1s are in 1? Just 1. So here we see the binary representation of the number 27. 1, 1, 0, 1, 1. To see if this makes sense to you, quiz yourself by trying to convert some other numbers into binary. Try these. Try converting 42, then 100, then 255 into base 2 binary. You can get back to me if you have any questions about this, or I'd love to hear your answers.